All right, we're going to talk about Cryptography 101. I'm going to show it. So I happen to be a C# developer, ASP.NET developer. So I'm going to show the code in .NET 6. I do have slides or a link at the end of the slides where you can get the slides. And I have two versions of the code. I have .NET full framework in 4.8, and I also have the .NET 6 code. So I just converted it to .NET 6 about a week ago. So I've not taken advantage of a lot of the great C# features in there yet, but I just ported and got it to run successfully. So the other note is what you're going to learn today is applicable across all sorts of languages and frameworks. So I'm going to show you in .NET 6, but these concepts are things that you could use anywhere. So if you've got good language, good frameworks, these things should be available to you in there. So it's important to understand the conceptual parts. A little bit about myself on there. I have my Twitter, I have my email and blog information. And like I said, I'll show at the end again that information along with a link to the slides and the code. So let's get started. So cryptography is the science of keeping messages secure. So if I were to ask the typical developer, why do you want cryptography? Most of them focus on the first one, which is confidentiality. So when they think about cryptography, they think about hiding data so it can't be read. And obviously that's very important, but there's three other goals as well. One is integrity, and that's where we want to verify that the data has not been modified. We use it for authentication. We want to be able to identify and validate a given user. We use it for non-repudiation, which just means a sender cannot deny later that they sent a message. So we're going to focus on that with digital signatures. And why it's important to understand your goals. I'm going to show throughout the talk specific techniques, and I'm going to map them back to goals because I see a lot of people in the cryptography that are picking the wrong techniques given what their goal is. So I see people using encryption when they really want hashing or vice versa. So it's important to think about what is your goal? What are you actually trying to get out of using cryptography so that you're sure you're using the right techniques. In .NET, it's in the system.security.cryptography namespace. The other warning we'll talk about in a bit, the .NET full framework, by the way, and the .NET 6 are very close to each other. There's just a few differences I'll call out throughout the talk. So you also want to think about these considerations. So again, understand what your goal is because that will drive what techniques you want to use. You need to think about your primary threats. So I run an e-commerce site, or I work on an e-commerce site, so I have to worry about typical things. I have a web server sitting on the internet, so I obviously care about in transit. So I'm going to be using HTTPS for all of my websites, as you should as well. I also, though, know that my web server, I've got firewalls, web application firewalls. I do security testing, pen testing, all that kind of stuff. But I could be exposed to a 0-day where somebody could basically own my web server. And if that were the case, they could access my config files. They could do a dump of memory, which for .NET, things that I've stored in variables but not yet garbage collected could be visible. So potentially passwords, credit cards, etc. They could modify pages, so they could actually change some of the page content and deploy it. They can also reverse engineer my assemblies. So it's not hard with ILDASM. If you're putting secrets in strings, people can easily use tools like ILDASM and reverse back from IL and be able to see what your secrets are. So you just need to think about how would someone attack me. So I just did recently another capture the flag competition. And if you've never done that, very informative. So I've known for years, because I work on an e-commerce site, I need to protect data. I've known for years the basic rules about SQL injection and everything else. It's very different when you're the person attacking and actually using these techniques. So if you haven't done a capture the flag, it's helpful. But more what it did for me is it just had my eye open to how someone might attack me. So it's important for you to consider how that would happen. And we'll talk throughout the talk about how you can deal with that. You're going to have company security policies. I'll talk about that briefly. You're going to have regulatory compliance. So I take credit cards, so I need to worry about PCI. You also want layered defenses, and you have to decide how many are enough, right? If I wanted to be completely secure, I would shut my web servers off, put them in a lead box, and put them in the corner. But that doesn't really help us run a business, right? I need to balance risk and reward but I want to have layered defenses. So I'm going to talk throughout the talk. I kind of think of it as a funnel. Without any security, it's easy for people to take over and do things against your website. By doing another layer down, I can cut the number of people that are capable of attacking my site. And again, this isn't just about websites. The demo is websites. It's anywhere you're using cryptography. But by using layered defenses, if someone's able to conquer one, I know I have one more behind it. So you need to think about how many do I need and what makes sense. If you don't take anything else from this talk, please don't write your own cryptography. So I've met developers that have thought that, where they said, it would be better for me to write my own encryption because I won't give out the algorithm, people won't know what it is, and therefore it'll be secure. I've read a lot about very serious cryptographers that have done very good work in the past. They still have issues and they have errors. So it's something if you're interested in working in cryptography, get involved with a project where you can work with other peers and people are doing security reviews. So again, just don't write your own. There's good cryptography built into, for me, .NET and other languages take advantage of that. I wanted to mention this, how .NET algorithms are implemented. As we look through the code and you look through the documentation, you'll notice that some of the classes end in suffixes. So if it ends in managed, that means that it's written most likely in C#. If it's CNG, it just means it's a wrapper around Windows Crypto Next Generation. And if it's Crypto Service Provider, it's wrapped around the older Windows Crypto API. So I just wanted to point out in .NET, it mattered what you actually picked. Those were meaningful as I just described them. If you happen to be using like .NET 6, all of those now wrap OS libraries. So regardless of what the suffix is, they're actually all wrappers around just the OS libraries. They're not any different. And the reason you care in .NET Framework, for instance, in the US, if I were doing government work and I needed to be FIPS compliant, the managed suffix classes, the ones that were basically written in C#, were never certified as FIPS compliant. So you just have to be aware that how they're implemented and what these suffixes are in .NET Framework, it makes a difference, and it might have an impact on what your goal is for the project. I also gave a link at the bottom. So if you are doing .NET 6 and you're trying to work cross-platform, be aware that, for instance, I work on Windows all the time. I could do all of my development, build it, test it, everything looks great. I go to deploy it to Linux and find out the class I had isn't actually available there. So check out that link if you're doing cross-platform. Just make sure the features you hope to deploy are in the platforms that you want to deploy to. You don't want to find that out at the very end when you've tested on Windows and then find out it doesn't work on Linux where you actually need to run it. So just be aware of that. We'll start jumping into techniques now. So the first one is what's called hash functions. So these are a one-way function. So they're very easy to compute, but they're hard, hopefully impossible to reverse. So as an example down below here, I've got a string. I'll compute a hash of it and I will get a set result. This is always a fixed size. So regardless of how big this is, the hash will always be the same size. It's going to be vastly different. So if I changed even one letter in here, if this is a good hash function, that right-hand hash will look completely different than it does. But the important thing is it's a fixed size, and that's driven by the algorithm I choose. So it converts that variable length to fixed. People call it a data fingerprint. Some people call it a digest. We're going to use it for both integrity and for authentication within cryptography. So in .NET, there's a base hash algorithm class. I've listed some of the subclasses here. I also struck out the ones you shouldn't be using. So MD5 has been broken for quite a while, so it's not something that you should use. Also, SHA-1 has been pulled and is no longer considered secure. So for me, for PCI compliance, we had to stop using SHA-1 a few years ago because it's no longer considered secure. So I'm going to focus on the SHA-2 family, and there's some different sizes in .NET, 256-bit, 384, 512. I'm going to focus on the 512. There is a SHA-3 set of hash algorithms. I'll just mention that. NIST was looking in the US, was saying we need another type of hash algorithm in case the SHA-2 family suddenly had issues. They wanted to make sure they already had another algorithm in place. So they basically ran a contest, said we want a new hash function that's implemented completely different than SHA-2. So they actually ran the contest. They've chosen a winner. I didn't list it here because it's not available to me in .NET. So from a company policy, my own personal philosophy, I'm not going to use things that are not built into the .NET framework because I want to know that it's been tested, reviewed, etc. So I might find George's blog that has C# implementation of SHA-3. That's not something that's going to fly for me to be able to use. Company policies, probably regulatory compliance, etc. So I'm just going to stick with SHA-2 because it is still considered secure and it's available to me in .NET. There also are keyed hash algorithms. We'll focus on the HMAC, SHA, and again, 256, 384, or 512. And we'll talk about why you want to actually be able to use one of those. So let's jump over to some code. So I happen to be, again, I'm using Razor Pages, C#. If you're not a C# developer, we don't need to focus so much on the specific syntax and the .NET part of this. The same kinds of classes will be available to you. So here I have a string that I just want to compute a hash of. So the first thing I'm going to do, I'm going to use SHA-512. Again, because I'm using .NET 6, I chose not to use these suffixes. So I'm not using the managed, I'm not using crypto service provider. I'm using the normal one that's going to work for me for cross-platform. So I create an instance of that class. First thing you'll notice when you work with .NET and cryptography is we all deal with strings usually, ints and other things. The cryptographic libraries in .NET are using byte arrays. So my first task is I need to take the string where my plain text is and convert it into a byte array. So if you look on the right-hand side here, I've got my plain text. I chose to use UTF-8. There's different encoding schemes. In my case, for the demos I'm going to do for you, I'm only working with myself, so it doesn't really matter what I choose. So I chose UTF-8. If you're working with a partner and you need to transmit information between each other, it will matter what you choose for this. So just make sure that you're encoding things in the same way. So once I do the UTF-8 encoding, the string now is a byte array, which gets sent to compute hash. And now I have a byte array that's 512 bits long in this hash value. Again, I don't want to deal with it as a byte array. I wanted to show it on a web page, so I'll just show you what this looks like on a web page. So here's the result. I wanted to be able to show the hash as a string on the web page. So that's the final step where I need to convert it from that byte array back to a string. So I'm going to show you multiple ways to do that throughout the talk. This one happens to use the bit converter class, and I put a comment here on how it works. It just takes each one of the bytes, represents it as 2-character hex with dashes between it, and then I just chose to take the dashes out, and you can see the result here. It's just a hex-based string that then I can use and display on a page. We're going to use this in various places, so I'll talk about when I might choose to use this encoding versus another. I think this looks clean and is easy to use. So again, that's all it takes. That's one of the advantages, again, of using a framework is there's not a lot of code. I've got a lot of comments in here for being able to give you the code, but very straightforward to compute hashes. I put the other plain text in here. If I were to uncomment and rebuild, even though that's a much larger string, if I came back to the page, the width would be the same because again, the resulting length is driven by my choice of SHA-512. So I want to show you practical ways to use cryptography as well during this talk. So the first one we'll talk about is what's called, I call it tamper-proof query strings. So the idea is I want to protect the integrity of the query string on my URL. So I want to make sure, I don't care if you see the values, but I don't want you as a client to be able to tamper with them. So you've probably been to websites where you look at the URL and it's got customer number equals 123, for instance. Somebody who notices that could easily go on the URL and change it from 123 to 124. It's likely sequential IDs, and potentially see other people's data, and that would be a problem. So the idea with this is when we construct a query string on the server, in my case, I'm going to append this hash of that query string and send it to the client. Then when the client clicks the link and comes back to the server, I'm going to recompute the hash of the sent query string and compare it to what it was when I first sent it to the client. And if those two don't match, I know that the client had tampered with the particular query string. So let's look at what that would look like. So here's my page. I'm going to click a link here. And if I follow this over, here's my query string. A equals 1, B equals 2, C equals 3. That would be the, for instance, of a customer number or something else. So again, we need to talk about goals. I'm not looking for confidentiality. These are not sensitive numbers. I don't care if you see them, but I don't want you to be able to tamper with them. So what I don't want is for you to be able to come here and change A from 1 to 2. And if I hit enter, it's going to blow up. So here's my first demo warning. Don't do this in production, right? I mean, I'm doing this for you, so during the demo, you're able to actually see how the errors are occurring. You'll be able to see things when you do the demo. It'll make sense that the query string hash values don't match. I don't want to give that kind of information to an attacker, and it looks horrible for a normal user of the website. They don't want to see stack traces and things like that. So just for the demo, I'm doing this and showing it to you, but it's not something that you would want to leak. So if I'm an attacker, I want to think, what would I do if I were attacking this site? Well, one thing I could do, I could try taking the hash off. Maybe they didn't code that right. You'll see the validation hash was not sent. If you think about it as an attacker, I can use hashing just like you can. So first of all, let's look at the code that we're using. So if I pull up the setup tamper-proof, so I just created a library function here. And so if we jump over to that, it'll look very familiar. So here, computing hash, I let you pass whether you want to use a key or not, which will become important in a moment. If you don't use the key, it'll just use SHA-512 like it did before. I'm using a key in this case, so I'm actually using this line, the HMAC 512. And the reason I'm doing that, we'll get to in a minute as we talk about attackers. My other demo warning, I have a secret here that you would never want to store like this in your code. Again, for the demos, I need a way to be able to have you run this. So that's why that's there. We'll talk about key storage and stuff later in the talk. It computes the hash like it did before. And then I give you the choice. Do you want to get it out as hex or do you want to get it out as base 64? So just two different ways to encode it. So if I'm the attacker again, let's go back to the page. I'll go to the original for it. If I were to click this and I start playing around with it and I realize I can't change these numbers, I can come to the end here and figure out that that's probably a hash, right? There's some protection here. You're letting me see the data. If I took that length, I could figure out it's 512. So I have access to the same hashing algorithms as you have. That's why in this case, I chose to use a key. So in the demo code, you'll see I have this hack tamper-proof. If I were the attacker, I would have tried to just compute a hash of the value that I wanted to send, and I'll put it in hex, and I could run this and get a result. So I could show you what it would look like. If I had A equals 2, well, then I could just take this, copy it. I could go back. I could change this to 2 like I want to, and then just change the hash. Right? That's what an attacker would try. And if I do that, we'll see it still doesn't work. And the reason it doesn't work is because of the key. So the reason I did the keyed based, we need to think like attackers and do layers again. Now I've made it harder, right? If I came back to this, had we not done anything, anybody could have come up to the URL and changed things, and that's really bad. So my first layer was putting this hash on here. That really cuts down the number of people that would even understand what that is. And any typical user on my site's not going to have a clue that that's a hash, and that's how I'm protecting it. So in the funnel, again, I've cut out a lot of people that can attack me. The people that could figure out that's a hash and compute their own hash, I've also dealt with them because now I have that secret. So you're not able to actually compute the same hash I did unless you're also able to get on my web server and steal my secret. So again, I wouldn't have the secret right here in a string, but it's layered defenses, right? I just want to make that harder for an attacker. So that is tamper-proof query strings. The other place we use hashing is for hash passwords. So when Unix came out, so I was doing research when I was in college on password security. When Unix came out, they were trying to design, we need to have passwords, we need to store them somewhere. How should we do that? And they were looking at encryption, which we'll look at shortly. But they had some issues with that. So they came and said, why don't we use hashing? Because when you type your password in, we'll compute a hash of your password. They then stored that hash in the etc password file. And so they have your username in there, and then they have a hash of your password. And the logic was because hash functions can't be reversed, that would be safe, right? No one would be able to attack them. And so they used this for their authentication. They made a couple poor choices potentially. So the password file on Unix is readable by anybody who's on the system. So anybody who has an account could pull that file. And that's what I was doing in my research. I pulled the password file. I know that I can't probably reverse the hash if it's a good hash, but the way I would attack it is what's called a dictionary attack. So I would guess that you were using a password that was from the dictionary. So I would actually pre-compute the hash of every word in the dictionary. Now I can just compare the hashed value against what's in the password file. And if I'm lucky, I'll get a match. And back then, it was about 60 or 80%, somewhere in that range, depending on the system, passwords that would actually get broken because they were dictionary words. So here's an example where I just took a hashed value out of the password file. And then up above here, I'm just trying to guess what your password might be. So in real life, they have password lists that you can get online that have just tons of password possibilities from real breaches and such. In my example, to make it simple, I just threw 3 of them into a dictionary. And then my crack password just tries to see is that hash actually present already or not. And if so, I'd be able to figure out which one of those words it was. So if I were to run this, you can see it happens to be secret. So again, I have not broken hashing. I was not able to reverse this value. But because they weren't thinking through how an attacker would attack them, they didn't realize that somebody could pre-compute all of those values and be able to attack the password file. So what are they going to do about this? Well, they decided we're going to use something called salt. So with salt, what they said is we're going to create some random data for each user, and we're going to store that in the user etc password file. So for each user, there's the username, the hashed password, and some unique data that they just chose to call salt. Now, when you come back and type in your password, I'm going to take your password and your salt value, compute a hash, and see if it matches the hash. So the cool thing was this made it where it was hard for an attacker to attack the entire password file, because now every row in the password file, they have to take the salt out and they have to recompute the entire dictionary using that specific salt along with every password guess. So we've just made it computationally a lot more difficult for somebody to attack the entire password file. So they said, well, that's cool. The problem is, if you think about it, it really didn't increase the security much for an individual password. So in other words, if I were attacking your password file and I got access to the readable file, I would look for users like admin or root or something that sounds important. I would use their salt and pre-compute, because if I can get that particular user, I can get the entire password file. So again, if you think about layered defenses, it was better than what was there before, but it still wasn't perfect. So I gave you an example here of how you could use that. So in this case, that's my password. There's some random salt. We'll talk about how to generate salt in a bit, how to generate this random data. but the rest of it is just normal hashing. I just take the data you give me and also pass into my function the salt that I want to use. So like I said, that made it better. It's harder for people to break in, but you might also want to do this. So this is one more layer again, right? I should use a key, or in this case, I'm just using another piece of random data that's secret that I'm also appending with a salt. So again, I wouldn't store it here in a string. I'd have it somewhere securely stored on my site, but by having this, it's made it that much harder. Now they don't have access to everything they need to compute the hash without breaking in. So again, for the funnel, I've just made it that much harder by using that. With all that said, how do people actually store passwords today? If you've heard of bcrypt2, in .NET, it's PBK DF2. You really want a hash function that you can make slow. You want to add what's called a work factor to it. So this is easier to show the code example for. So if we look in here, so I'm a Led Zeppelin fan, not my real password, but could be, right? Here's some salt. I'm going to use that class, but here's the magic of these classes. I'm going to look at my current hardware and I'm going to choose a penalty amount. In other words, I'm going to say I'm willing to make my real users wait, let's say half a second. So I'm going to take that half a second. I'm going to keep playing with this iteration count on my current hardware and try to get as close to a half-second delay as I can. Okay. The reason I'm doing that is I'm making it intentionally hard for an attacker. So I'm doing two things, and I have to do this trade-off. I'm making it slow for a normal customer too. So when they come back to my site and they type in a password, it's going to take them at least a half second because I'm making the hash take that long. But if you think from the attacker standpoint, they want to pre-compute a bunch of words from dictionaries and thank you very much, social media. I have your spouse's name, your kid's name, your dog's name, your favorite car. I mean, I know a lot more about you today than I ever have before. But by doing this iteration count, every time I have a guess at what the password might be, it's going to take at least a half second. So it's computationally now really difficult for me as an attacker to pre-generate the list of potential hashes for you. So again, it's just a trade-off. This is a one-on-one talk, so we won't get into all the details, but someday my hardware is going to get better and I'm going to have to adjust this amount. Well, if I change this amount, the hash value changes. So you got to think ahead about probably storing that count on your password file so that you know what was used for the particular hash so that you have a way to make it harder even in the future. So that is hashing passwords. So we're kind of through the hashing part. So I'm not sure if there's any questions from the chat we want to hit now. Otherwise, we'll jump into the encryption.
There's no questions in the chat at the moment.
Okay, thank you. So now we're going to get into what people normally expect with cryptography, which is encryption. So there's just some basic terms that you should know that are used in the industry. The first one is plain text. So that's my original data. We're going to do encryption, which is the process of obscuring my data. Ciphertext is my encrypted data. Decryption is the process to recover the original data. The cipher is the algorithm we're using, and we're going to use this for confidentiality. So there's two basic types for encryption. The first is what's called symmetric algorithms. So we'll look at this first. So if you look at the diagram, I have some plain text that I want to encrypt. So I'm going to encrypt it using a secret key. And when I encrypt it, I end up with my ciphertext, which is what people won't be able to read. That's the confidentiality. To decrypt it, they need to use the same secret key, and they'll get back to the original plain text. So that's why they call it symmetric, is because the same key is used for both the encryption and decryption phases. So this is great. Symmetric happens to be very fast. The problem is that that secret key makes things difficult in certain situations. So for instance, if I were to go to the participant list and pull one of you out and say, I want to send you a secret, the problem is I can't send you a secret without us having a shared secret key, but I also don't have any way to give you the secret key securely. So we're going to talk about how they deal with this, but for now, just know that that secret key has to be shared securely, but it's fast, the actual algorithms. So again, there's a number of different classes available. I'm going to focus on AES. That's still considered secure. It's probably what you'll run into most in industry. DES has been broken for a long time, so don't use that. Triple DES is either broken or very close. So again, I'm going to focus on using AES for this talk. In .NET, the symmetric algorithms are all what are called block ciphers. So the idea is I take my message, the plain text, and I split it into blocks. So I take a block at a time, and I'm going to encrypt that block. When I get to the very end of my message, it's not likely that my message is going to end exactly where the block size ends. So I need to put some padding in place, and there's different ways you can do padding. I will show you why I'm using this ISO. It adds the most randomness in the padding. I'll show you why you don't want to use things like zeros. There's also multiple modes that I can use with AES. The first one is called ECB. And what ECB does is it says I'm going to take the first block of plain text, I'm going to encrypt it, and then I'm just going to set it aside. I'm going to go do the next block. So I want to show you why this is a problem. The reason that it's not the best choice for modes is because the same data at the same spot will always encode to the same place or to the same value. So if we look, this penguin image, every white pixel here, it'll get encrypted and it'll end up being a different value. But if you can see, all the white ones end up as the same value. So if I use ECB mode and I'm only doing a block at a time and that's it, you can see that I can still kind of make out that that's an image of a penguin. If I use other modes, we'll see that you won't be able to tell that. So it just does not add the randomness that we want because it's not using a good mode. So there's another choice called CBC. And what that mode does is it says, I'm going to encrypt the first block of data, but I'm going to use the ciphertext output for that as random input into the next block that I want to encrypt. So even if two blocks in the plain text are exactly the same, their ciphertext blocks won't be if I use CBC mode. So that's why it's a better mode than ECB. And I'll show you that with a practical example. If you think about that, how does it get random data for the very first block to use? Well, that's what's called the initialization vector. And what that does is it's just random data that's used to seed the first block. It turns out the way the algorithm works, it doesn't need to be kept secret. You just never want to reuse it. So you basically don't want to ever use the same IV twice, because if you do, your messages that end up coming out will be the same. You've lost the randomness you were hoping for, and patterns in cryptography is a bad thing. So let's take a look at what this would look like in code. So I've got a page, I'll show you that as well. I'll just type in test, hit encrypt. So as what you'll notice, every time I hit encrypt, even though I have the same plain text, I'm using the CBC mode. So I end up with different ciphertext and I end up with a different initialization vector. So that's why that's good, even if it were the same value, because otherwise, if it always turned out the same ciphertext, people can eventually learn patterns and understand potentially what it means. I'm not giving them anything because I'm using a decent mode. And then I can decrypt it back to the original. So again, I would send this and that, and the person who has the secret key would be able to do the decrypt. So let's look at this in code. So I'm going to focus on the encryption part here. So when you click the encrypt button, it calls this method. First thing I want to do is I need to have a cipher. I want an AES class. So I created this common function to do that. Again, there's multiple. I'm not using the suffix classes. I'm just using, since it's .NET 6, just the AES.create. I listed out the defaults there for key size and modes. So I'm changing the padding mode to the more random one I talked about. Here again is my secret key. Again, don't do this. Don't store it like that. This is for the demo, and I'll show you how you can generate the random keys in a moment. So once I have the cipher, Every time I create an instance of that AES class, it's creating a random initialization vector for me. So all I want to do here is show that initialization vector on the screen. I chose to use a different encoding here called base 64. It's very common. You'll see that it typically, you'll see it ending in some equals, so you can know it's base 64. But that is the encoding. So instead of using hex, I just chose to use base 64 to show you that there's multiple options. Then I create an encryptor. I still have a string. I need to convert it into a byte array. You've already seen this. And then here's the actual cryptography. And then again, I base 64 the byte array for the ciphertext back to a string so I can show it on the page. So again, this is AES is very solid as an algorithm. It's a good implementation in .NET, and it's not a lot of code. And again, within a company, typically somebody will write a wrapper so that you just say, here's my string key, and it will do all of this for you, but it's not a lot of code, which is again, why you want to use what's in the framework and not try to write your own stuff. It's not hard to call this stuff. So that's what we want to use, and we want to use that built in. So again, that's symmetric encryption. We'll talk about some keys quick. So I did put in the demo code. There's a get bytes. So if I were to call this, I'll show it to you in the web. If I just keep hitting refresh, this is a different AES 256-bit key every time. So that's where I get my random key I want to use. And you can look through the code for this. So here's the only thing that popped up for me in .NET 6. I've been using this random RNG crypto service provider for a really long time. So if you know things about random numbers that are built into typical libraries, they have a random function. Really not that random. So they're poorly seeded and they don't give out a good random number sequence. So they're not considered secure. When you do cryptography, you have to make sure you use what's called a cryptographically strong random number generator. So since the beginning of .NET Crypto, it was RNG crypto service provider. .NET 6, you can see my squiggle here. It's telling me there's a new class, random number generator, that's also cryptographically secure, and I should switch my code. So that's one of my to-dos here. But I get bytes and I return it as a hex array in my case. So this generates my key. So again, it's a cryptographically strong random number generator, but if you know how computers work, they're never totally random. So I was reading up on Cloudflare one day. If you're familiar with Cloudflare, obviously a huge internet provider, does a lot of reverse proxies for people. They actually have a wall of lava lamps in California. And when they need to generate some random data, they actually take a picture of the current state of these lava lamps. So they're reaching outside the computing system, which is not random, into the environment. And they took the digitized photo of the state of all of these lava lamps as part of their randomness to figure out their random data, which I thought was kind of cool. So again, let's look at why using the other mode would be bad. So I'm just going to stop my web server here quick. And I'm going to make a few changes to our cryptography here. So in this case, I'm going to switch this to be zeros and use ECB mode, which we talked about why that's not a great idea. And I'll kick off my web server here. And when I go recreate this and make my request again, so what's happening? This is why you don't want to do this, right? Every time, test always becomes the same ciphertext because I chose a poor mode. So I just wanted to show you why that choice matters. People can see me sending this and might be able to figure out patterns associated with what I'm telling the person I want to do. I'm going to mention this. Again, this is a 101 talk, but today people have been moving to, there's a new class of algorithms that are actually combining hashing with encryption. So if you look at this AES GCM, you can follow through the code here. It's not much more code, but what it does is it does the confidentiality you want with encryption, but it also computes a hash of that ciphertext. So when you give it to someone else, they can make sure that it's hasn't been tampered with first, and then they'll be able to use the decryption. So I would say today modern systems are probably leaning more into these algorithms that do both. And so it's authenticated encryption. And so AES GCM. So again, it's a 101. So I'll just show you the code is here, but be aware that that's something that combines the best of hashing with encryption at the same time. Okay, so we looked at symmetric. So now we talked about the problem with that is that we have a secret key. And so how do you get the keys distributed? So they came up with this other type called asymmetric algorithms. So with this, the idea is that each person that wants to participate will create a public-private key pair. They're going to keep the private key, obviously, to themselves. They'll give out their public key so others can use it for encryption. So if we look at the diagram, if I wanted to pull one of you out of the participant list and send you some data, I would get your public key. I will take my plain text, encrypt it with your public key, and I have ciphertext. Now, as soon as I do that, I cannot even decrypt this. So the only person that can decrypt that is the person who has the corresponding private key for the decryption to get back to the original plain text. So that's the idea with asymmetric. Some people say it solves the key distribution problem. I wouldn't say that. I would say it lessens the issues with key distribution. So if I wanted to send to one of you, would I trust your public key in an email? No, right? Emails are postcards. People could change that and change that public key. Would I trust it on your LinkedIn profile or maybe your Twitter profile? As long as I believe those sites are using good secure practices and using HTTPS, I have more confidence that that's your public key. So again, it's not perfect. The risk here is still that I have not your public key, so the attacker could use the private key and decrypt it. So I just need to make sure I get this, but there's better ways for me to share. There's a number of classes in .NET. I'm going to focus on RSA. The negative of this, again, it makes the key distribution better. The problem is the encryption is limited in how much data it can encrypt, and it's about 1,000 times slower than symmetric. So it's an order of magnitude slower is the negative. I might as well pull up the code and show you how it looks in the site. So here again, I'll type test. Here's my ciphertext. I do decrypt. I get back to test. See what that code looks like. Same idea. I have an encrypt function. So first I want to create a cipher again. So I create an RSA. In my case, again, I just have their public key. So this is not so much a confidentiality thing anymore. I would probably have a database with a customer and here's their public key, or an employee or a vendor or whatever. I could store this stuff in a database because it's public keys. So it doesn't matter if someone can see it. And then down here, I do the same things I did before. I need to change my plain text string into a byte array. Here's the actual encryption, and then here's the ciphertext. So again, very powerful and not a lot of code. So now I have securely done that encryption that only that receiver will be able to decrypt. And notice I did put a comment in here to use this padding with RSA. The default padding is no longer considered secure, so make sure you use this one. But again, and then decryption is very similar. So we'll see that that was not a lot of code. That was pretty straightforward to write. Again, the negatives are it's not a lot of data and it's a lot slower. So let's think about it. I have a website, a public website on the internet that I want to take credit cards, for instance. If I look at my options, I want confidentiality, so I know it's encryption. I could use symmetric, but if I did that, I have to store a secret key on my public web server, which I told you at the beginning, I consider compromisable. So I really don't want to do that. So what I can do instead is I can create an RSA key pair. I can put the public key on my web servers. So as soon as you come, I will encrypt your credit card with my public key. Now I have ciphertext. The only person who can decrypt that is the corresponding private key, which I won't have anywhere accessible from the internet. That's going to be behind my firewall, very secure system, very limited access, etc. The only person, that's the last step before we call the credit card processor. That's the only place the private key has to be available. And again, it's only for small amounts of data, which for a credit card would be fine. So let's look what that would look like. So I come to the web page. I'm going to type in my credit card number there. Watch, I'll just happen to luckily hit a real one. I should just. So that is my ciphertext. Now I can put this and store that in a database or a queue or transmit it around, because I know the only person who can decrypt it is the one with the private key. So inside I have a system that reads that and is about to call our credit card processor, and I can decrypt it at that point. So it's a good technique. Again, we think about attackers. We've avoided the key storage issue by using asymmetric rather than using symmetric encryption. So there's actually credit card processors today typically will generate a key pair like this. They'll give your company just the public key and they keep the private key. So nowhere inside my company would I be able to decrypt that data that I encrypted with that public key. Now I can send it fully encrypted to the credit card processor. They are the only ones who have the private key. They can get the credit card number back and authorize the charges and such. So that's basic encryption, both symmetric and asymmetric, with some practical examples. So now I want to talk about digital signatures. And what this one does is it's going to provide both integrity and non-repudiation. So the idea, let's say I have a contract I want to send to one of you in the participant list again. I want to make sure that you get it and that it hasn't been tampered with. And you want to be able to prove that I'm the one who signed the contract. That's the non-repudiation. I should not be able to say later that I didn't send you that contract. You'd be able to prove that it came from me. So the way you do that, if we look at the diagram, well, I'll throw in one more thing. By default, digital signatures do not provide confidentiality. So in other words, when I send this to you, someone could still read the actual contract. So for my demo, I'm going to throw all of this together. I also want confidentiality. So we're going to just look at the diagram below. The plain text is encrypted with the receiver's public key. So we just saw that. That's just standard asymmetric encryption. Once I have the ciphertext, I'm going to compute a hash of it because I want integrity. So now I have a hash. The signature is actually, I encrypt the hashed with my private key. So this is first time you see this, and this seemed weird at first, but the keys are interchangeable. I can use either for encryption or decryption. So I'm going to sign it with my private key, and then you have a signature. Now I can send the ciphertext and the signature to you. You'll be able to prove that it wasn't tampered with. You'll have confidentiality, that no one read it, and you'll be able to prove that I'm the one who sent it because I'm the only one who has my private key. So you have my public, you'll be able to prove that I was the one who signed it. Let's take a look at what that would look like. So I just have an example. In this case, I'm just sending a link to a vendor on the web. And so if I click this receiver, I'm sending it on query string parameters. So here's my secret. This is the ciphertext. And if I were to go further over to the right-hand side, you'd see my signature. And then the person who received it would be able to get back to the credit card number. So let's take a look what that code would look like. And we'll just focus on the sender for now. So I need two different things here. I need the public key of the receiver because I chose to do confidentiality and encryption. I need my private key in this case. And again, this is just how RSA keys end up exporting as XML. That's why it looks like that. And again, I wouldn't want my private key stored here. It's for a demo. So first I'm going to create a sender cipher that has my private key. I'm going to create a receiver cipher that has the receiver's public key, which we'll see here. And then a lot of this will look familiar. Here's my credit card. I need to convert that into a byte array. I'm going to do the same encryption you saw before with RSA. So now it's encrypted as some ciphertext bytes. I want to compute a hash of that. So this is what we saw with hashing. And then here's the new part. This class in .NET is what does the signature for me. So I say I want to use SHA-512, which is a SHA-2 hashing function, which is good. And I want to create the signature. So it's computing a signature off the hash I have of the ciphertext bytes. And then I can do, in this case, I did base 64. And because I was sticking it on a URL, I had to encode it. And that's my ciphertext and signature. And that's what got added to the URL. So again, not a lot of code to do a lot of stuff. So we know it's not read, hasn't been tampered with. You can prove it came from me. I'll show you briefly what the receiver looks like, kind of the reverse. They pull the secret off, they pull the signature off the query string. They have to take it from base 64 back to byte. So this matters, right? I'm talking a partner situation here. So we had to agree to use base 64 and we had to agree to use SHA-512. They compute a hash of the ciphertext and compare. And they're using the public key that of me because I sent it. And they call this function down here. And it verifies the signature. So it makes sure that the hash sent, that it was signed by me. And then it does some more decryption of the data and then gets it back as a string. So again, that's a good practical example of a lot of stuff we've seen, the hashing, the confidentiality, and then the addition of digital signatures. Another place you'll see all of this come together is HTTPS. So if you have a website today, you should be using HTTPS to make sure people in transit not only can't see your data, but also not tamper with it, not add malware and stuff in between the browser and the server. So the way that works, if I'm a public website, I will create a public-private key pair. I will take the public key and take it to what's called a certificate authority. So I've used Let's Encrypt, which is free. I take my public key, I go to them, they say, prove you own the website. There's a number of ways to do that. They might have me drop a file in the root folder. They might have me add a DNS record, whatever. Once they're confident that I actually own the website, they will digitally sign my public key along with information about me as a company. That becomes what's called the certificate. Browsers know about these well-known certificate authorities, so they know about Let's Encrypt and DigiCert, whoever else, and they'll trust certificates that are signed by those certificate authorities. So if we look at what happens between a browser and a server, the browser talks to the server, so this is TLS. It says, I want to use HTTPS with you. It gets the server certificate. It validates that it was signed by one of its trusted certificate authorities. It then has the server's public key. Now, it could just do asymmetric encryption right then, but we know that that's slow and it doesn't do a lot of data. So what they do is they call it hybrid encryption. They use the server's public key. They'll generate a brand new random symmetric key to use. They will encrypt that symmetric key with the server's public key, and they'll send it to the server. So the server is the only one who can decrypt that, so it decrypts. Now both of the two ends have a random symmetric key to use for this session. Then they drop down and use symmetric encryption because it's fast. And so they're talking to each other using symmetric encryption. So again, it's a combination of asymmetric to get around the key distribution, and then using symmetric where it's fast and does a lot of data. Talk about key sizes first. So key sizes are really, it's a trade-off between performance and security. So if we look at AES, AES supports 3 key sizes. Lowest is 128 bits, highest is 256. As you add more bits to the key, somebody who's trying to break AES, assuming you have a good implementation of AES. So the algorithm is still, as far as we know, not broken. I'm trusting .NET's implementation of AES. So the way someone's going to try to break my symmetric AES is they're going to try to brute force guess my keys. The larger the key size, the harder that is for them to do. So it's not twice as hard to go from 128 bits to 256. Every bit I add makes it basically exponentially harder for them. So I want to use the largest key sizes I can. So I use 256, 4096. Just do some testing for yourself. I've done the testing of 128-bit versus 256-bit, very negligible from a time impact, and I don't want to get fired, right? From a security standpoint, somebody breaking my 128-bit key when I could have used 256. So that's my philosophy. I'm going to use the largest key sizes I can. Talk about key storage. By far, to me, the worst part of cryptography, right? You have secrets and you need to store them, in my case, on a web server that you're admitting somebody else could completely own and get admin rights to. That's a problem, right? This is a 101 talk. I don't know where you all deploy all of your code, so it's hard to say what you should use. I would say there's no perfect solution to this. There are things like Azure Key Vault and other systems that, again, have some layered defenses in place that are better than putting your key in the string like I am for the demo, right? I personally avoided this by doing the asymmetric trick. So when I need to take a credit card, I like the public-private key, put the public key on the web server, because at that point, I'm not concerned if you break into the server, it's a public key. You're not going to have suddenly a secret that could decrypt a bunch of traffic you've been watching for the last month. I would just have to figure out you broke into my server, take it down, put back a different public key next time, if that makes sense. So again, in summary, don't write your own cryptography. Use what's built into your library and languages. Use trusted algorithms and implementations. Again, I want to know that it's been vetted, that other people trust it, it's been tested. Make sure you know what your goal is. So use hashing if you want to validate the integrity of your data or to prove you both know the same secret. Use symmetric algorithms unless you have special needs for asymmetric, only because it's so much faster and they can do much larger amounts of data. The asymmetric is really limited in size. And again, the special needs would be you have key exchange, you need digital signatures, etc. And lastly, again, make sure you know your threats and choose proper countermeasures. So think through how someone would attack you. As you saw, the original hashing a password seemed like a great idea. They didn't think about the dictionary attack, so they kind of had to keep trying more things. So just make sure you think through how someone would attack you. I'm a Pluralsight author, so I do have an introduction to cryptography. So that happens to be in .NET full framework. It's like 2 hours plus. In the middle section, I have a number of books that are good. I like the practical cryptography in Python. I don't know Python, but why I like that book is it talked about a lot of the algorithms I talked about and specifically spells out why is MD5 broken? What part of that is the part that's bad? So it had a lot of practical advice of how you should use cryptography today. The next three, they're all interesting. So I don't personally care how AES is actually implemented. So I don't care about all the bit shifting and all the math, and I'm just not interested in that. I use those books because they go into that detail. If you are interested, you could figure all of that out. Or if you're implementing AES for something and needed to do it, you could see the specs and how it works. But they also talk about how to use it properly. So I used it more for how do you use AES, you shouldn't use DES, those kind of things. The last set of books, if you're interested in the history of cryptography, so how did it start with Caesar cipher, Vignette cipher, all those other ones, how people broke them, the cryptanalysis techniques that were used, how the cryptographers changed to make it better, how is Enigma broken, all those sorts of things are in these last two books, which are cool for that. And again, that's my Twitter, my email, my blog. That's a link to the slides and the code. And again, you'll have full .NET Framework 4.8 or .NET 6 versions. Again, I have not tweaked and optimized for 6, but it's built for 6. And we have time now if anybody has any specific questions they'd like to go through.
Rex has asked in the chat, are a loaded question.
Okay.
Are the paid SSL certificates in the market safer than the free Let's Encrypt?
Oh, that's a great question. So you can get certificates, like you said, from Let's Encrypt or from vendors where you have to pay. The cryptography that you get from both of them is the same. In other words, the certificate is the verification of your public key. You still have to worry when you implement HTTPS, which is really, HTTP on top of TLS. You have to choose all the ciphers that you want to support. So I recently switched to TLS 1.3. It's a lot faster. That's where you get issues. How you choose which ciphers you're going to support in TLS is really where the secure part comes in. But Let's Encrypt certificates are just as good as ones you're paying for from another vendor. If that makes sense.
Thank you. Thank you.
I have a quick question.
I'll mention one other thing.
So go on.
The Let's Encrypt is, the difference is it's all automated too. And so you have to get used to, like I had to get, I think it's Certify the Web. I got software that would do the auto updates because they're only 90 days, not a year. And so that's some of the trade-offs with free versus not. Some companies don't want to have to rev their certificates or have them automated. So that's part of that decision. But yeah, that's the same. It's really your cipher choices that control the security. So sorry, go ahead. What was the next one?
Well, just catching on that point you just mentioned, I think that I could often see in companies where they pay for the longer one, maybe it's like 2 years, but then they forget about it. And in 2 years' time, basically the site goes down. And actually, if you automate it more regularly, that's less likely to happen. So,
yes. Yeah. And that happens a lot more than you would think. I mean, I'm trying to remember that there was another major vendor. So we had an issue with one of our vendors where their certificate just expired and caused me issues on my site. But I think they've cut down those 2-year certificates. They've pulled into, I think the most you can get now is a year. But yeah, it's people, when it's that long, they forget, right? And so suddenly the day comes and your certificate is expired. So that's really unfortunate. So yeah, the automated helps with that because I can kind of fire and forget. I go check it occasionally just to make sure it's keeping up. But that is the nice part of the automated ones.
I quite like, I know I mentioned Kubernetes at the start, but there's an add-on for that which does it all for you. You've got one line to install it and it keeps it updated. It just calls out to Let's Encrypt and just adds it all and just does it for you, which is pretty cool.
That is pretty cool.
So my question was just, you mentioned a few times that you don't want to use a certain type of padding or there's a few different settings that maybe you could accidentally set wrong in code. Do you find that IDs have good linting to like obsolete attributes, that kind of thing, just so you know that you're not using the wrong one?
So that's a good question. So I have not seen specific cryptographic linters or analyzers for like my C# code that's looking to say, hey, you should move. So let me go I'll pull up this example. I mean, .NET happened to do that for me in here. Like when I do a build now in .NET 6, they've now deprecated this one. So then I get this kind of a warning. But as far as the padding and stuff, there's nothing telling me. So let me go find that example, like the RSA one that we were talking about in asymmetric. I did not know that the base default padding that .NET used was not secure, and I should use this. I got that out of that practical cryptography with Python. So I had to get that somewhere else. It'd be nice. I think you're asking like, and I haven't seen them yet, is there an analyzer that I could add to my Visual Studio or VS Code or whatever that would say, hey, you're using an insecure technique here. You shouldn't use ECB. I haven't seen that before. I think that would be great if they had it. I go further where I say, why do we still have MD5 in here, right? Why does .NET just say, forget it, it's not secure and we're not going to have it in our library? And I know that the argument will be that you do work with partners or older systems, that's all that they have. But I would sure like, and I guess I haven't honestly tried it in .NET. I'd love to, if I tried MD5, I'd love the .NET compilers to say, that's a really poor choice, right? But I don't know security specific scanners or linters or things that have good baked in knowledge about the crypto stuff. I mean, the things that I've seen have been from reading those 4 or 5 kind of dense books, and that Python one especially recently, saying that, here's why MD5 is broken, and then I just need to remember that as I'm doing my stuff. I want to set company policies like that, and possibly I could go in if we had a corporate, we run these analyzers. I could put in a rule to say, I want to look for this within my own company and say, you better not be using this or this or this or that. I just haven't seen an industry one that I could recommend that would do that for you, if that made sense. Is that kind of what you're going for?
Yes, yeah. It feels like it should be out of the box though, because it's kind of
Yes.
if you accidentally put the wrong padding on that line there, it feels like it should be squigglies there showing you. It seems a bit.
Yes, yeah, it would be nice. And in fairness, they're doing it on the one, right? The get byte ones. I mean, they know now that they don't want to use this anymore, so they deprecated it. And there's, how things work in industry. Not everybody agrees either, right? Like when MD5 was first broken, there were people that said it's not broken, and there's a camp that says it's broken, and here's why. So it takes a while for the industry to eventually coalesce around, yeah, MD5 really is bad. Like I said, I haven't tried it in here. I hope it gives a squiggle. I'll probably try that later and see, did .NET, when it's clear, like NIST and others say MD5 is dead, I hope they do squiggles, but I haven't honestly checked it because I know not to use it, I guess. So.
Yeah, Phil's just said in the chat what I was thinking pretty much. Sounds like a good opportunity for someone to write an analyzer.
Yes.
Yeah, it's kind of just creating one, put it on. I suppose the problem is you actually need to know your stuff to write in the first place.
That's the problem is, and it was difficult for me until I found that practical book. I had seen people talk about some stuff, and I'm sure that the stuff that's in there, I haven't found a good source yet that is definitive to me, right? I wish there was a site that said, you definitely can't, this is definitely wrong. That would be the best source. But within security community, some things they'll say, like everybody will say, don't use MD5. I think that's pretty universal today. Some of these other ones, like the example I gave with AES, I started out with the simple example first because it's what most people are used to, right? Just doing the CBC, and that's better than ECB and all that kind of stuff. But today people are saying, you probably want to shy away from that and use these authenticated encryptions where you get the hashing and stuff. People are starting to say that now. But yeah, I would also be concerned if I wrote the extension about the legal liability. If I'm saying you're fine with, AES, whatever, and tomorrow it gets broken, I wouldn't want to be in that position. But
how concerned do you have to be when quantum computers become more of a thing?
So that's a good question too. So quantum computing, and I didn't get into a lot of it here with asymmetric, but asymmetric with RSA and the other asymmetric algorithms are all based on mathematical things that are difficult to compute today. And so like factoring primes, elliptical curve calculations, those are the basis of the asymmetrics. And they say when quantum computing is available to everyone, those math functions won't be difficult anymore. And so there's been talk within the industry for years that, quantum computing is going to kill everything we do today. There's also people saying that we could write better algorithms to do the encryption on quantum computers. So it's back to that, the arms race between the good and the bad, whichever side you're on, right? Whichever side you consider good. I'm on the good means good encryption, right? That is the concern, is quantum will make it where, especially the asymmetric ones, those mathematical functions will be simple. And people have warned that potentially when quantum's out there for everybody, RSA is toast, right? And so is the elliptical curve. So we're going to have to watch as that plays out. I'm hoping somebody comes up with new algorithms and techniques that will be hard still on a quantum computer. So we have time to get ready, if that makes sense.
Because if you think about all the stored encrypted data that's just out there, and in the future, anyone can potentially access it, so it's quite scary.
It is very concerning. So I keep an eye on that, and I read that when I see stuff about quantum computing as well. And I'm not up on how soon that will be will that ever be in my laptop on a, something that everybody will have, or is that just nation states, which they probably know how to break some of this already anyways, right? Back to thinking of your adversaries and who you're protecting against. There's people that are super determined, might have the kind of resources already today for some of the stuff that we use. So we do the best we can, right? With what we have.
I'm out of questions. Has anyone else got any? Feel free to unmute.
And I'll show my info again. When you get the code, and if you see things or you have questions and want to follow up, you can reach out to me on any of these as well. So
we can put all this stuff on the website as well. We've got .NET.com, which we put every single meetup we've had and all the links and videos and everything.
Okay.
Cool. So if no one else has any questions, I'll just wrap up saying a big thank you, Robert. It's been really good having you talking about cryptography. It's quite interesting stuff. I'm certainly interested in some of those books you mentioned. It's kind of obviously echoing what you said about don't write your own. Yes. I would never do that, but I'm kind of like quite interested to just do a bit of reading on it anyway, just out of curiosity. I remember I used to listen, like I've not listened to it in years and years, but there was I think it's still going, but Security Now podcast.
Okay. Yep, I haven't heard of that.
Yeah, he used to go, Steve somebody, I can't remember his second name, and he used to like go in, like talking about like all the bitwise stuff, which was quite interesting.
I like Darknet Diaries is a good podcast now about security and people breaking into things. It gives you the perspective of attackers and what they do. So that's also a good podcast for that. But yeah, as a hobby, I like reading about that stuff too. It's kind of cool. So I appreciate you letting me speak to your group today.
Well, thank you for joining us. Interestingly, the Darknet Diaries I hadn't heard of until very recently. I saw someone mention it in a podcast. Sorry, not a podcast, a blog post. So I'm gonna have to start listening to that.
Yeah, it's interesting.
Cool. Okay, so just to echo what Matt said in the intro, I just want to thank the sponsors, which obviously Curricula have been our sponsors from the start. As Matt said in the picture, providing drinks, which we unfortunately can't do anymore, but maybe one day. Everstack, my own company, the prize draw sponsors JetBrains, Manning, and Packet. And they said Oscode, that's a very old sponsor. So yeah, JetBrains, Manning, and Packet. And really sorry about the prize draw not working. And sorry for meetup.com not working as well. I can't really say anything about meetup.com going down, given the prize draw app went down as well, but we'll try and get that sorted for next time. Matt did actually suggest beforehand us rewriting it in Blazor, so that might be we've got a goal for the next meetup to rewrite that in Blazor, so that should be good fun. Thanks everyone for the prize draw email. So I will get that drawn tomorrow and email the winners from that. We've got a few emails too, which is good. What else? Oh, thanks Matt for being my marketing department in the intro talk. Great job.
I'm assuming there's some salary or something coming away for this at some point. But
I feel I should after that. That was fantastic.